Welcome to the math record. This video will be a continuation of our previous video summations on polynomials over exponentials. Okay, so in our previous video, we used the summation, the infinite geometric series of x is equal to 1 to infinity of 1 over a to the power of x to equal 1 over a minus 1. And then we use that to get our linear, which is x equals 1 to infinity of x of a to the power of x is equal to our a divided by a minus 1 to the power of 2. Now, in this video, we're going to be covering the quadratic and the cubic. So let's do this in order and start with the quadratic first. Okay, so what is this? Well, when we were working with the summation in our previous video, how the numbers look like were like let's say it was x over 2 to the power of x, right? So it was like 1/2, then 1/4, 1/4, then 1/8, 1/8, 1/8, right? And then 1/16, 1/16, 1/16, 1/16, and then 1/32, 1/32, 1/32, etc., right? So then we see that there was missing terms there. And that's how we were able to make a summation horizontally for these. And then we could make a summation vertically going down because it was just missing the first, second, and third. Now for a summation with a quadratic, when we're working with this, because it's going to be generally the same thing, but now there's going to be like a scaling factor. So let's say this is x squared, right? So now it's going to be like 1/2, 1/4, 1/4, 1/4, 1/4, right? And there's got to be 1/8, 1/8, 1/8, 1/8, etc. And there's 8 of them. I mean, there is 9 of them, I mean, right? Because 3 to the power 2 is 9. So how I'm going to write this is that instead of writing the numbers, because it's going to be kind of tedious, I'm going to use a placeholder to represent a number. So this guy would represent 1/2, and then this guy be 1/4, then this guy be 1/8, and this guy be 1/16, and 1/32, and so on. So the first sequence, and when we put x equals 1, is 1/2, so there's only one of them. When you put 2 here, there's 4 out of 4, so this one has 4, 2, 3, 4. And then when you put 3 here, that's 9, so that's 9 out of 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then when you put 4 here, that's 16, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So as you see, there is the same sequence, right? The first sequence, the second sequence, the third sequence, the fourth sequence, right? But these sequences now has multiples of them, right? The first sequence has only one. The second sequence has 3 of them. The third sequence has 1, 2, 3, 4, 5. And the fourth sequence has 1, 2, 3, 4, 5, 6, 7, right? And if you keep going on, it should be 9, 11, etc., right? Which you could kind of see because if you kind of put in the numbers for x, it's going to be 1, right? And then you put a 2, so that's a 4. Then you put a 3, that's a 9. You put a 4, that's a 16. You put a 5, that's a 25. 4 minus 1 is 3. 9 minus 4 is 5. 16 minus 9 is 7. And 25 minus 16 is your 9, right? So then the next one's 36, right? Because that's 6. 6 squared is 36. 36 minus 25 is 11, right? So it's going to keep coming out as as these common difference, which makes sense because the difference between each current term and the next term of a quadratic has the same constant. That's just the fundamental principle of a quadratic, the most basic. So since we know that it follows this pattern of 1, 3, 5, 7, right? And it kind of works for every single one of these exponentials, then what we could do is that we could set up the equation, right? So it's 1. So when it's the first term, it only has 1. The first sequence only had 1. The second sequence had 3. The third sequence had 5. And the fourth sequence had 7, right? So we know the common difference is 2. So we got to put 2x. Sorry. And then we put a 1 here. So that's a 2. So the equation is 2x minus 1, right? Put 2. That's 4, 3, 6, 1, 5. And then 8 minus 1, 7, right? So it's following this equation. So we're going to put it in the same formula as what we did for part 1, where we have a summation inside that's doing horizontal and a summation out, and there's a summation outside which goes for vertical. So we have a summation. I'm just gonna write x on the outside, and then we have 1, right? Because when we were writing our sequences, right? 2, 3, 1, 2, 3. Okay, right? And then there's like 5 of these, right, etc. I'm not gonna write the precise, right? It was like 1, 3, and then 5, right? Because they were grouping them together, right? So 1, 3, and the 5. So as you see, it's increasing as it goes down vertically. So it goes down 1, then it goes down 3, then it goes down 5, which I didn't put in, and then it goes down 7, etc., right? So we're not going down horizontally. So our vertical variable is going to be our x, and our horizontal is going to be n. So instead of writing our variable, so our variable is x, right? Which we wanted to keep x because we're working with the vertical, because the vertical variable is x, and the horizontal is going to be our n. So we have a summation of n is equal to our x, right? How we wrote it from part 1. And then we have 2x minus 1 times a 1 over a to the power of x. I mean n, right? So it's basically the same idea. If you kind of ignore this, it's basically just the linear, but now every single sequence might need to be scaled up because there might be like what the first sequence might be only one of them, and the second sequence has 3 of them, the third sequence has 5 of them, right? So you just have to scale it up. So as you see, if you kind of think about it, this number which you scale up it's um is kind of a constant, but it's just relative to the sequence. So what I mean is, let's say we have the first sequence, right? So when we have our first sequence, oops, okay, when we have our first sequence, it looks something like this. And then we have our second sequence, right? It looks something like this, which has 3. I'm not gonna write it precisely the amount. It's fine. And then there's like 5 of the next one, right? So when I mean relative, right? This sequence only has one of this. This sequence has 3 of them. So the constant is 3, right? I mean, the constant is just this one sequence, but there's 3 of them. So that's why it's relative to that constant, because there's 3 of them of this one. Now let's think about this one. There's 5 of these. So the constant for this is relative to this, which is 5. So this constant is never going to change, but it's changing vertically down. It's just not changing when it's moving horizontally. So what we could do is that we could just move it outside, but it's actually not going to affect it. So we have 2x minus 1 outside, and then we could just do that summation inside. We have 1 over 8 to that. So what's our first term? Well, we just plug in n is equal to x. So x is our first term. So it's 1 over a to the power of x, right? And then it's going to be 1 minus 1 over a, which is just, this is the same thing as a minus 1 over a, right? Which you could just write over a. Dividing by a fraction is also multiplying by its reciprocal. So it's just a over a minus 1 over times 1 over a to x, which is what it's the same thing we use for our linear. Right? So it doesn't really matter. It's basically just simplifying the entire time. But it's just a repeat process, which I'm showing step by step. Okay. So we have 2x minus 1. Okay, so, and this one was a over a minus 1 times 1 over a to that, right? And this thing, which we talked about, is a constant, because a is a constant, so this has to be a constant. So we just can move this outside the summation, which I just delete the rest of these so then I can get some room to work with. Okay. Okay, so we have a over a minus 1 times a summation x equals 1 to infinity of 2x minus 1 times 1 over a to the n. And then to find this sum of this, oh well, if you kind of think about it, we could just split it up into two summations. We could split it up as 2x over a to the power of, oops, sorry, this was supposed to be x. That's x. So 2x divided by a to the power x, where x is equal to 1, right? Because when we put in the n, we substitute it with the x. I'm sorry about that. I forgot to change it. And then x equals 1 to infinity. And then we have 1 over a to the x. Okay, right? So I just split this up because this is just 2x minus 1 divided by a to the x. So it's just 2x divided by a to x minus 1 over a to x, right? So we can split it up into two summations with the same bounds from 1 to infinity. So what's this one? Well, you could just do a substitution in because we already know what it is. It's just 2, take out the 2 and put it in front, right, of our summation. And we know x divided by a to the power x is right here, right? Because that's what we solved for already in our previous video. So we could just substitute that in. And as you see later on in this video, that every single time we're gonna to find like a high-level polynomial, we need everything else before it. So you want a cubic, you need a quadratic, linear, and a constant. And if you want a cubic, you need the quadratic and also the linear and the and our constant. So it actually takes so everything that you need to find for the next polynomial, you actually have to find all the polynomials before it. So it's kind of like a recursive function. And then this one, a to the power of x, is just this one, right? Which is what I mean when I said that statement like a second before. If you were paying attention. Okay, so we have a over a minus 1 times 2a over a minus 1 squared minus. And then you multiply a minus 1 on top. So then you have a minus 1 squared on the bottom. So we get the same denominators, so we could be able to simplify. Right? Delete. Move this and move up. And then now we get able to simplify and then just make a really easy equation. Okay, so now we don't have any more summations. So 2a minus a is a, minus a negative 1 is plus 1, and then a minus 1 squared, which simplifies to a times, which I like to just use parentheses, but I just wrote times there just so you could know. So a times the a plus 1 and a minus 1 cubed, right? Because it's a square and that's just a power of 1. And that's just a minus 1 cubed. So that tells us that's just going to be a times a plus 1 over a minus 1 cubed. So we're kind of seeing a pattern when when we're doing these summations of these polynomials over exponentials, right? We see a constant here, but it's not here. Just don't worry about that one. There's an a here and a here. And we see an a minus 1 as a linear, then as a quadratic, and then as a cubic. So and it's gonna be probably a logical assumption that you could say that the next term, which is x to the power of 3 over a to the x, that summation is gonna give us a cubic on the bottom, a quadratic on the bottom, right? Which would make sense because it kind of follows this pattern. There's probably gonna be another a there, but what we're gonna do is that we're actually gonna have to prove it again, right? So we have a summation where x is equal to 1 to infinity. We have a summation of n is equal to x to infinity, and we have to find out what we need to put here. So let's think about this with like another scenario. So we're gonna use the same thing like case again. So x cubed to divide by 2 to the power x, and then remember, right? We could just plug in numbers here and then find out what that difference is. So if you put in x is equal to 1, that's 1. So the first sequence only has 1. Now you put in the second sequence, right? That's 2. That's 4, that's 8. So there's 8 of them. So we kind of draw that thing out. So the first one, when you use 1, and then when it's 2, you're going to have like 8 of them. So 1, 2, 3, 4, 5, 6, 7, 8. And you put 3 of them, that's 27. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right, etc. There's 27 of these. So I'm not going to write them all out because it's kind of tedious, right? Because this is 8 and this is only 1. So if it's 8 minus 1, that's 7. That means there must be 7 of these now. Okay? So what you could do is that you could always use the next term minus the previous term to get the actual amount of sequence there is of that sequence, right? So that's 8 minus 1. So let's keep track of that. So that's 1 and 8. And the next one is 27, right? So that's 3. 27 minus the 8, that is a 19 and 4. And if you put 4 here, that is a 64. 64 minus that, 27 is 37. Let's put a 5. That is 125 minus is 61, right? 125 minus 64 is 61. You put 6, that's 216. 216 minus 125 is 91, right? So now we know what this is. So does this follow like a conventional pattern? Well, if we look at it, it's definitely not linear. So if we kind of do the difference, that's 6, that's 12, that's 18, that's 24, and that's 30. Now it seems like it's following a pattern now, right? That's 6, that's 6, that's 6, and that's 6. So it's definitely following a pattern. It's just not linear. What it is that it's going to be following a quadratic because the second difference is constant now. So what that tells us is that we actually are following a pattern that's similar to our quadratic here, but is that it's now instead of a linear, the multiples of a particular sequence as it goes down vertically is actually going to be like increasing, which makes sense, right? Because this is one power more, so it's going to be increasing by like a difference that is one further than the previous one. So if this one was the first difference, that means the second difference is constant, is what I'm saying. So as you see that, remember what I wrote down, which I can erase, I don't know why. We have 1, 1, it was 2, 7, 3, 19, 4, 37, and 5 is 61, I believe, right? Because that was 6, 12, 18, and 24. Yeah, that's right. I'm trying to remember what it was. Sorry about that. 6, and this one was 91. Now you put this in your calculator and make it like a regression where this is the x and this is the y, right? You should come up with the equation that's quadratic, which is 3x squared minus 3x plus 1. So I'm not going to prove in this video why that is true. Just trust me on it. It's just it's just a equation. It's just a regular polynomial, which if you take an algebra, should be relatively simple to do, right? Which I don't know why you would be finding out how to do a summation if you're just doing algebra, but it's pretty interesting to think about for this. So it's just that pattern, that multiple. So whatever the amount of multiple is, times a to the power of n, right? Because n is our horizontal, so we have to put that inside. And our vertical outside is our x. Okay, so now let's derive this equation. As I said before, you can move this one outside because it's constant relative to the actual sequence. So we have 3x squared minus 3x plus 1. And then that is times the summation, oops, to infinity, a to the power n. Sorry, that doesn't look like a summation. I kind of write my summations like e's. And then we have x equals 1. Okay, 3x squared minus 3x plus 1. And I'm not going to do that proof again. I did previous time for like our linear and our quadratic in this video. In our quadratic, I did that proof with our quadratic in our linear. I did it in the previous video, which you should know as a over a minus 1 times 1 over a to the power of x, right? So then, like usual, you can move this one outside. So then it's just be a over a minus 1 times the summation from x equals 1 to infinity. That looks bad, right? And then let's just write it as like an actual combined function. So 3x squared minus 3x plus 1, and then you put the a to the power of x on the bottom, right? So that seems simpler to do now, right? So instead of having a linear, we're going to actually be working with a quadratic, which is why I said if you want to find the higher-level polynomials, you actually had to use the ones before it. Because now you definitely, to find a cubic, now you actually have to use a quadratic, right? So we have, okay, we have a over a minus 1 times, and then we can split this up, the summation up from 1 to infinity, right? You have to keep the bounds the same. 3x squared over a to x. Remember, this is in parentheses. It kind of looks ugly, but it's fine. Summation from infinity, x equals 1, on 3x divided by a to the power of x, plus, right, plus summation from x equals 1 to infinity of 1 over a to the x, right? So a over a minus 1 times our summation from 1 to infinity. We already know what this one is. It's just 3 times the quadratic 1 over the exponential, which is what we wrote here, right? Which we just derived earlier. So a over a plus 1 over a minus 1 to the power 3 minus 3 times our linear, which is also right here that we put on the side, a over a minus 1, which we derived in the previous video, plus a our constant, which is just a regular infinite geometric series. Okay, so let's simplify this. A over a minus 1 times 3a times a plus 1, which is 3a squared plus 3a, right? So I'm just skipping some steps so we don't have to like spend more time on this because we just need to get the formula. And then we need to multiply a minus 1 on the top, so we get a minus 1 cubed on the bottom, right? So it's just 3a times a minus 1. And that should factor out to 3a squared minus 3a. 3a squared minus, 3a squared plus 3a, right? Because we need to keep that negative out here. So we have a minus 1 squared. Actually, no, never mind. That is a minus. Sorry about that. Minus 3a. Right, because this is a minus right here. Okay. Cubed. Right? I'm just simplifying. Like it's like working with fractions. So you have to get to add like fractions that has different denominators. You gotta make the denominators the same first, right? And then you have to multiply a minus 1 squared, right? So then it makes a minus 1 cubed. So a minus 1 squared on the top is just a squared minus 2a plus 1. Just a minus 1 squared. Okay, that's power 3, which I don't have room for another parentheses. So let's kind of write it out a little over here so we get more room. So 3a minus 3a, that cancels out, so we just have this a squared. And then 3a minus a negative 3a, that's 6a, plus this negative 2a is plus 4a. And then the only constant is that plus 1 over a minus 1 power 3. And that should simplify relatively just a times a squared plus 4a plus 1 all over a minus 1 to the power of 4, which is what we predicted to be for this, right? This is linear, quadratic, cubic, and now it's a quadric. And then we have a squared plus 4a plus 1. Oops, sorry, that looks like a 9. That's a 4. A minus 1 to the power of 4. Okay. Sorry about that. I'm coughing. Okay. So we have all these equations. So what we did in this general process of how to get these equations, it's basically you're going to have a summation outside or x is equal to 1 to infinity. You use any random variable. Just keep your variables constant throughout so you know what you're working with. So then you have your n is equal to your x. So this variable has to be equal to this variable. These two have to be exactly the same. Okay. And then that also goes to infinity because they're both infinite geometric series. Because one's infinitely going to the horizontally and one's infinitely going vertically. And then we have some kind of like pattern that you gotta have to find out, right? So it's like depending on each sequence, how many of those patterns are there? How many like multiples are there? And then just find that pattern and then plug it in here. And then that's gotta be uh put in as a over x. A over n. And then you can keep simplifying that equation and you should get more of these numbers. So a easy trick that I kind of seen with these coefficients that if you imagine a as a coefficient of 1, right? This is 1a, which is just a, right? It's a coefficient of 1 and then a is 1 and that coefficient is 1. And this coefficient is 1 and this coefficient is 4, 1. If you kind of see this, it kind of looks like Pascal's triangle, doesn't it? It's 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, right? And it continues going on. But it's not exactly a Pascal's triangle, right? And you're right, it's not a Pascal's triangle. It's actually something called a Eulerian triangle, or a Eulerian, which I'm not exactly sure. A Eulerian number triangle. So I'm not exactly sure if this is the exact term, but basically how the triangle kind of goes is that you're not going to be using factorials precisely in a way, but you're going to be using the summation idea, which I'll send you the Wikipedia page on the descriptions if you want to look. So it kind of follows this 1, 1, 1, 1, 1, 4, 1, and then 1, 11, 11, 1. And it's got to be 1, 26, 66, 26, 1. And then there's got to be more numbers, but I'm not going to put them because some of them are kind of really big. But it's generally going to figure out this pattern. And this pattern tells you what's going to be the next one. So if we had to find x to the power of 4, right? What's x after 1, 4, 1? was this one, is 1, 11, 11, 1. So it's actually gonna, you can see the pattern. So A, so we're gonna have an A here. And then we're gonna have A cubed, right? Because this one's linear and this is quadratic, so this is cubic. So A cubed plus 11A squared, right? To keep the coefficients the same. 11A plus 1, right? So 1, 11, 11, 1 divided by, and on the bottom, we know it's going to be a power to 5, right? Because this is linear, quadratic, cubic, quadric, so this one has to be a power 5. So this would be our x to the power 4, which is a really interesting thing to think about if you kind of see these triangles. So instead of proving it, we kind of see this general pattern that like mathematicians already have solved, and then we could just put that pattern into use to see these connections that might like exist in the world around us. So I hope that was a really interesting video or like idea that you could like think about when you want to like see concepts that you think sorry about that. See concepts you think that might be kind of like basic that you could extend further into like higher level like mathematics. Well, thanks for watching, and if you like the video, put a thumbs up, and if you have any com comments, put it in the comments below, and maybe I can answer them. Thanks for watching.